So now we're going to talk about a couple of other types of reactions. That was precipitation reactions. And we're also going to talk about acid-base and gas evolution reactions. And these can also be predicted by doing the just swapping ion partners. So an acid-base reaction is a reaction between an acid and a base, right? Kind of in the name there. Also called a neutralization reaction because the acid and the base neutralize each other. And the products are generally water and a soluble ionic compound. Gas evolution reactions, which we're probably not going to get to today, a gas is evolved, meaning a gas is produced. It's often seen as bubbling. Many gas evolutions are also acid-base reactions. As with lots of things, some of these reactions can fall into more than one category. So, acids and bases. We said that an acid was an ionic compound that formed hydrogen ions in solution. There are more specific definitions, and those will become a little more important in Chem 1B, but we'll introduce you to this name here. Arrhenius. This was a scientist, so it's his definition of an acid, a substance that produces hydrogen ions in aqueous solution. So that's the definition of acid that we've been using. And here we see HCl. HCl is a molecular compound, but when it's dissolved in water, it forms ions. It ionizes. So it forms hydrogen ions and chloride ions. That doesn't describe what's really happening, though. If we think about a hydrogen atom, it has one proton and one electron, right? When it becomes a hydrogen ion, H+, it loses its electrons, so what's left? A proton. Just a bare proton. So I think of these hydrogen ions as being like babies, like little tiny babies, like 3-month-old baby, right? Too small to be out by themselves. Did you see any 3-month-old babies out on the sidewalk? No, of course not, right? If you did see a baby, somebody was pushing it in a stroller or holding it in their arms, right? Or they had it in the car and they're driving it around. So the hydrogen ion is just a bare proton, and that is like super, super reactive, and it's just not going to be alone. What happens is it's going to attach to a water molecule. All of this is happening in aqueous solutions. There are gazillions, literally, of water molecules around. So when this proton, this hydrogen ion, leaves the chloride, it doesn't have to be alone. There's water molecules everywhere. And so it's going to essentially ride piggyback on a water molecule. So you've got the H2O with an extra H plus on it, and that gives us H3O plus. And that has the name hydronium ion. So that's what's actually happening. Now, it gets a little tedious having water and hydronium ions and stuff in all of your equations. And so we tend to use H plus and H3O plus interchangeably. And I know that's a little confusing to students, but it's unavoidable. So I think of the water molecule as sort of the babysitter. It's holding the baby for us. But we really don't, who the babysitter is doesn't exactly matter. Was the baby around or not, right? But the baby's never alone. So that's my weird analogy for that. Polyprotic. Poly means many, and protic refers to protons. So polyprotic acid has many ionizable hydrogens, many ionizable protons. And so it can release more than one. An example of this is sulfuric acid, H2SO4. And we see in the beginning of its formula, H2, there are 2 hydrogens. This is a diprotic acid because it can release 2 protons, 2 hydrogen ions. It does those sequentially. It releases one, and then it releases the next. It doesn't release them both at the same time. So what happens there is you get the H2SO4. And that will release one hydrogen ion, and then what we have left is the hydrogen sulfate ion. The hydrogen sulfate ion also has an ionizable hydrogen, and so that can also release, and then we've got SO4 sulfate. So this is sort of the fine print. Sulfuric acid is one of those that I listed as a strong acid. It's strong in its first ionizable proton, meaning all of the sulfuric acid molecules will lose one hydrogen ion. And so mostly what you'll have is hydrogen ion and hydrogen sulfate ion. It's weak in its second ionization. And so this one only goes to sulfate a little bit. I just feel like I have to tell you the whole truth about that. Bases. So the Arrhenius definition of a base, substance that produces hydroxide ion in aqueous solution. So the most obvious ones are metal hydroxides, things like sodium hydroxide. This is an ionic compound, and it dissociates into sodium ions and hydroxide ions. So there's the hydroxide ions. There are also bases like ammonia, NH3. You look at that and you're like, how's that going to make hydroxide ion? Well, it does it in sort of a backwards way. So ammonia mixed with water. What happens is the water is going to lose one of its hydrogens, and we're going to form ammonium ion and hydroxide ion. So the ammonia pulls a hydrogen ion off of a water molecule, and so the result is we have produced hydroxide ions, and so therefore ammonia is a base. It is a weak base. Some bases can produce more than 1 mole of hydroxide ions per mole of base. An example is strontium hydroxide. So when the metal ion has a charge that's larger than +1, when this dissolves, we get strontium ions and 2 hydroxide ions. Okay? And these happen all at the same time. It's not release one and then release the other. They just release them all at the same time. And we have no special name for those sorts of bases. It's not a dihydroxy base or anything like that. So the neutralization happens when we get the hydrogen ion from the acid combining with the hydroxide ion from the base. So here we have hydrochloric acid and sodium hydroxide. And we can think of this as being one of those swap ions formulas or swap ion situations. So the acid forms hydrogen ions and chloride ions. The base forms sodium ions and hydroxide ions. So if we swap partners, we get the sodium with the chloride and the hydrogen with the hydroxide. Hydrogen and hydroxide together make water, and sodium and chloride, it's going to be soluble, it's going to be NaCl aqueous. The acid had hydrogen ions in it. The base had hydroxide ions in it. When they neutralize each other, now we don't have hydrogen or hydroxide ions present. The net ionic equation, when we have a strong acid, always ends up being H plus OH minus to make H2O. Any questions? There's some illustrations of acid-base reactions. So here we have the HCl and the sodium hydroxide. So in this test tube, we've got hydrochloric acid. So here's the chloride ions, and those hydrogen ions are actually riding on water molecules. So you have this hydronium ion. And then in the other test tube, we have a sodium hydroxide solution, and we have hydroxide ions and sodium ions. So when we mix those together, this water molecule with the extra hydrogen, the hydronium, it's like he's carrying around this baby, and then over here there's a water molecule that doesn't have its child, right? It's missing a hydrogen. And so they're like, hey, this is messed up. So we'll give this hydrogen ion to that hydroxide ion, and then we've got two water molecules. So all of this acid-base business is about hydrogen ions being passed back and forth. So all of the hydrogen ions neutralize all the hydroxide ions, and what we have left is just sodium and chloride ions. So we took an acid, HCl, and depending on how concentrated it is, that could be pretty corrosive and dangerous. We got sodium hydroxide, which is also dangerous. It's used as drain cleaner, right? It'll dissolve your skin. Really good on hair clogs. If you have hair clogs in your bathroom, get the drain cleaner that has sodium hydroxide in it. Eats through them like nothing. So both of those things could be really dangerous to you, right? You mix them together in the right proportions and you've got salty water. Now you might want to not drink that, but you could swim in it. It's not going to hurt you at all, right? So here are some common acids and bases. And this is where the book finally tells you which ones are strong and weak. So there's our 6 strong ones. HCl, HBr, HI. What do these guys have in common? It's a binary acid with a halogen, right? Chlorine, bromine, and iodine are all sisters. They're in the halogen family. And these are the bigger sisters. Down here, we have another halogen sister, fluorine. HF is also an acid, but it's a weak acid because fluorine is the little baby sister, and so that one's weak, and the others are strong. I really got nothing to help you out with these 3. Nitric, sulfuric, perchloric, just remember it. Anything else is going to be weak. So we don't have to write the state symbols here. But I'm still going to write my ions down here with their charges so that I can predict the correct products and get a balanced chemical equation, because it's got to be balanced. Here we've got a diprotic acid. Now, sulfuric acid does release its hydrogen ions one at a time, but when we're titrating it, we're going to react all of those hydrogen ions. So when we're talking about, looking at the final products, just take all the hydrogens off and you've got sulfate here. You don't want to do it with hydrogen sulfate. And then we're going to swap partners and put them back together. H plus and OH minus. Oops. That's water. And then my other 2 are K plus and SO4 2 minus. And so the charges on those ions tell me that this formula has the is K2SO4. We could write state symbols, but I don't feel like it. Yes?
So the H2,
Mm-hmm.
the hydrogen is the one that's going to react in 2 phases.
Right.
So that's why we're not worried about writing H2 and when we bring it down. We're just writing
Yeah,
H2.
we don't need to be worried about the 2 stages here, because the first one comes off, and that's going to react with the potassium hydroxide. And once all of that is reacted, then the second one will come off as it reacts with the sodium hydroxide. Yeah, so we don't need to worry about it.
Is that only in titration or just all the time?
That's mostly in titrations. Yeah. Okay, so I need to balance this equation. When you have a diprotic acid, you're going to need some coefficients, because I have 2 moles of hydrogen ions here. I'm going to need 2 moles of potassium hydroxide. So if I look around here, I see I've got 2 Ks over here, and I'm going to need a 2 in front of my KOH. Sulfate and sulfate, I have 1 of each. And then I have a total of 2 hydrogens here and 2 more hydrogens, so a total of 4. So I'm going to need a 2 in front of my water molecule. And then I've got 2 oxygens here that aren't in the sulfate and 2 oxygens that aren't in the sulfate. Then I'm going to erase this because I don't need the rest of this to do the stoichiometry. So I need to start with a balanced chemical equation. And usually in these problems they give it to you, but we're just getting some extra practice. So now I'm going to use that equation to organize the information. 20 milliliters of H2SO4. So 20 milliliters of that. And it says 22.87 milliliters of the KOH. And the concentration of the KOH was 0.158 moles per liter. And don't write capital M. It's an abbreviation. Write what it means, moles per liter. And what am I trying to find? Concentration of the H2SO4. So that's going to be molarity. So this is stoichiometry. I've got a chemical reaction and I've got amounts of stuff. So I'm going to start with grams to moles to moles to grams. That's always the starting point. Sometimes, like on this worksheet, there were some problems where you just get rid of the grams at each end and you just have moles to moles. It's supposed to make the problem a lot easier and faster for you, but it ends up confusing you because you're like, grams have to be in here somewhere. And so then you try to make it all hard and you do it wrong. Moles in the middle is always there. Mole to mole, always there. And then what's on the end might be different. But start with grams to moles to moles to grams. Am I starting with grams of anything? No. I've been told I've got this many milliliters of the KOH, right? And am I trying to find a mass at the end? No. I'm trying to find moles per liter. What I've got here is milliliters. What I need something about the moles, right? So I don't need to do this last step at all. So here we've got milliliters and liters getting all mixed up together again, right? And this is going to happen most of the time because we measure stuff in reasonable quantities using milliliters, but molarity is moles per liter. But if we look at this molarity that we're given, 0.158 moles per liter, that means that 0.158 moles is equal to 1 liter of solution, right? So if I make that smaller by a factor of 1,000 and say millimoles per milliliter, have I changed the ratio? No. Because I put the same thing in the top and the bottom. I could cancel them out if I wanted to. So this is using millimoles. The advantage of this is that I can use this molarity without doing any unit conversions, just by putting milli in here. And then I don't have to convert my milliliters to liters. So what I'm doing up here is I'm doing milliliters to millimoles to millimoles. Then I'm going to take my millimoles and divide by my milliliters, and I'm going to get molarity. Just watch. So this is my starting thing that I know more information about. So I'm starting with the KOH. Let's maybe make a note of that up here. I'm starting with the KOH, and I'm finding out about the H2SO4. So I'm going to go milliliters to millimoles to millimoles. So 22.87 milliliters of KOH. And I'm going to convert that to millimoles of KOH. And then I'm going to go to millimoles of H2SO4. So I'm going to have milliliters down here and millimoles of KOH down here. Millimoles per milliliter is the same number as moles per liter. So this is 0.158. The mole ratio, I've got 1 mole of sulfuric acid to 2 moles of potassium hydroxide. That's the same as 1 millimole of H2SO4 to 2 millimoles of KOH. If you don't like millimoles, you can convert to liters and do it that way. That's not my calculator. So I've got 22.87 times 0.158 divided by 2. 1.80, oops, 673 millimoles of H2SO4. And that should have 3 significant figures. When I do these calculations and get millimoles, the numbers are nicer. If this was moles, it would be 0.00180673 moles. So I've got my millimoles of sulfuric acid. I want moles per liter. So I need to take the moles and divide by the volume. 1.80673 millimoles divided by 20.0 milliliters. Like, but that's millimoles per milliliter. You want moles per liter. Cancel out the M's. There it is, moles per liter. So I got my 1.80673 divided by 20. 0.0903365 moles per liter. We'll round that to 0.903. And I can write moles per liter or 0.0903 capital M. Any questions?
Just so I'm on the right track conceptually here, It makes sense that potassium hydroxide would have to be at a higher concentration because the H2SO4 is a dipronic acid, so it's releasing
Right.
the other.
Yeah, so sometimes we can look at the results here and identify whether it makes sense or not. Other times it's like, it's too hard to think about. But here we have very similar amounts of these two solutions. And so the concentration we got for the sulfuric acid is significantly less than that of the KOH, which makes sense because we need twice as many KOH molecules as H2SO4 molecules. So this would have to have a lower concentration and a higher concentration since the volumes are similar. The reason that M1V1 doesn't work here is it doesn't take into account the stoichiometry. If you happen to have one-to-one stoichiometry, it'll work. But if you don't, it won't. And I guarantee on the exam, it's not going to be one-to-one stoichiometry because I know you want to use M1V1 and I'm going to get you. Okay? Any other questions? The 0.0903.